value that is larger than t min, but you're doing it in the wrong way. So you weight in the wrong direction at most 2 times t min, and then you switch to the other direction and weight another t min. So altogether it's 3 times t min, and sum it all up. It sums up to 8 or 9, whatever you said over there. It's fine. The answer over here, and I think that we are done with this one. Any question about homework 2 that is approaching? Good. Can we get an extension of homework 2? Yes, I will not wait with publishing the new homework, but as usual, we can squeeze a few more days. And let's talk about, I don't need you anymore. And let's talk about So we discussed the network flow. And again, it's really, really useful to know network flow because there is so many other problems. Some of you will get, of course, in homework 3, that you can solve if you know how to phrase them as network flow problems. So going over what is a network flow problems, I'm giving a graph that is directed. With every edge, I'm getting the maximum capacity of this edge, say 2 gallons per minute, 1 gallon, 3 gallons per minute, and so on. That would be the maximum flow that can pass through this pipe, or change it into bits, and it would be the maximum flow of bits that I can send through this channel, through this link. I'll have a source that is producing water or bits, target that is the destination. I want to send as much flow from S. That is what my optimization function would be: send as much flow from S, send as many more bits or gallons per minute from S. A little lemma that we will not prove at this point of the course will be whatever you are sending, whatever the amount of flow that you are sending from S, it's exactly the amount of flow that reaches T. So that would be exactly the amount of flow that receives T. And what's the limitation? What's the problem at all? So we need to discuss what will be the flow inside every channel, such that all the other nodes that are only behaved as routers, they don't have any place to store water or to produce water or to eliminate water, or as routers, they are memoryless. All they can do is just take a package and route it to one of the directions outside. But what's the limitation? Take all the amount of water that you receive, and you need to make sure that when you send it outside, you are not exhausted one of the pipes. You cannot send along this pipe link. I can send other 0 bits per second, kind of contradicting my aim to maximize the flow. But I can use it to just send 0 bits per second. I cannot send bits in the negative direction, it's directed. Or I can send 1 or 2 or 3, but if it's 3 bits per second, it's fully utilized. 4 is not allowed because the pipe only allows 3. So if we look at this problem, here is so I'm going to write next to each edge in blue what is the flow that we want to send in this little problem. Again, our aim is to maximize the flow, but keeping the 2 types of constraints. The capacity constraints, don't send along a link more than the maximum you can, and the flow conservation constraint. For every node, every node that is neither S nor T, the amount of flow reaching into this node must be equal to the amount of flow that this node pushes to the outside. And it's up to us to determine what will be the flow per every edge. So what's our option? We will use this edge to send, it can allow us to send 300 bits per second. Why not doing it? So we'll send 300 along this edge. What about this edge? It allows 100 units, but if we send 100, we cannot get out of it because this edge only allows 50. So should we try 50? And then we can send 50 over here, but then this node has an issue. There is 50 gallons arriving every minute, but it can only send a maximum of 2 plus 3 from this node. So the maximum actually that I can send cannot exceed in this direction more than 2 plus 3. So I'll only send 5, 5, 3, and 2. And I didn't tell you what about these edges. It will be 2 and 2 as well. Right? So that's how we need a design for this flow. Lots and lots and lots of research about flow conservation. Of course, many applications, from networking all the way to wireless networking, all the way to traffic of cars, all the way to many other problems that flow solves. Again, we'll see plenty of other applications. But how do we solve it if we have access to linear programming? Linear programming will just say, this problem just lends itself, it's right itself. What are we trying to do? We want to maximize the value of the flow, which is the net flow that leaves the source. So that would be my cost function. That is, what is the flow that I'll call PUV will be the flow along the edge, UV. So here, my cost function would be maximize P from S to D plus P from S to B. That's the flow that is leaving it. Subject to, for every node that is V, set of vertices, minus the source, minus the sink. T is the sink. So for every node that is normal one, which is a router, the sum of the PUV, it's variable for the ILP. Don't let this strange notation confuse you. Just call it XI. the sum of the POV along the edges that are entering this node D should be equal to the amount of flow that is leaving the node D. But you see here an example, a legit flow. If I look at, oops, I have two Ds for some reason. So if I look at this D, there is all total of 1 plus 1 flow going in. Remember, the first number is the actual flow. The second number is a capacity. Flow of 1 plus 1 going in. So it receives 2 gallons per second, and it got rid of 2 gallons per second. Along this edge, flow of 2, so this node checked. And that's the ILP. What if it's actually, if you are sending bits and for some reason you really want an integer number of bits? Well, you can always put integer next to the variable. It might run much slower, but it's definitely legit if you want an integer flow. If you're talking about bits, probably doesn't have any impact. Just solve it as a linear programming. If you're talking about tracks over there, and this is flow of, and these are all depots of tracks that you are arranging over there, then or containers, then maybe you do want integer solution because you don't want to split a container. Like physical container, not program, computer. Okay, switching to another problem. Wait, still in the network flow. Why there are algorithms that solve these particular problems very, very efficiently. It's one of the highly investigated problems with its many variants. And there I have pretty fast polynomial time algorithm. Why do I send you to use linear programming or integer linear programming instead? Well, because of the flexibility. There is many variants of these problems that you might want to solve in real life. And either there are no algorithms or not polynomial algorithms, or you just don't know if you trust a code that you download from the web is trustable or not to solve other problems. LP, you are trusting, and it will give you the optimum. What type of problem do I have in mind, for example? We were working on problems that it was a communication from wireless nodes, yet information that arrives from sensors to nodes, and we cared for communication, and then the impact on this wireless node, there was an impact on the battery that depends on the radius of transmission. So I had cost associated to each bit that I'm sending depending on what's the destination. So there are various costs or weights involved in it, which you can easily throw into the LP, but much harder to solve we're using one of the existing nice algorithms like Ford and Falkerson or Edmonds Karp that you might have seen in undergrads 445. Maybe we'll get to them in this course. Okay. Vertex cover. Vertex cover in a graph. Again, one of the very, very famous problems. You are given a graph, and I want graph consists of edges, vertices, and I want to pick a subset of the vertices so that I cover all the edges. It's always confusing, is this edge cover or vertex cover? Because am I covering edges with vertices, or I'm covering vertices with edges? So vertex cover refers to you're covering edges with vertices. To cover an edge, it's enough that you'll pick one of the two endpoints of this, any one of the two vertices that this edge is adjacent to. So, but I want to make sure that every edge is hit. I want to pick a set of vertices so that for every edge in my graph, at least one of its two endpoints is in the graph, is in the set, in the cover. Solution, take all the vertices, you're done. Well, yes, it's true, then I definitely hit all the edges, but I want the minimum such set, the minimum set that will hit all the edges. So NP hard, so not very likely that you'll be able to find an exact solution. Okay, 1 point increase in the grade if you're getting any reference to movies. Anybody? No? Okay. Any reference? Any guesses? I'll do it again later. Okay, so how do we do it if we have ILP? It's really easy, right? What we want to do is to set for every vertex vi, I'll set a variable xi, and if this variable xi is 1, then it means that the vertex vi will be in my set cover. If xi is 0, then vi is not used. What do I want to minimize? I'm trying to minimize the sum of the xi's, the sum of the vertices that I used in the cover. What are the constraints that determines my feasible region? My feasible region would be, or my constraints would be that look at an edge vi, vj in the graph. Look at an edge, say, between B6 and B5. What must happen in your cover? Either B5 must be picked, or B6 must be picked, or both. That's also fine. That is that for this edge, vi, vj, xi plus xj, both of them are Boolean, 0 or 1. Their sum must be larger than 1. So at least one of them, if they are Booleans, must be 1. And that's the ILP to solve the vertex cover. But we are going to stay a bit more on this problem. We're not done with this problem completely. Everybody agrees that once you run it, every xi is an integer between 0 and 1. Between 0 and 1 is a linear constraint. It's two linear constraints, actually, larger than 0 but smaller than 1. And these linear constraints that you're generating for every edge. So if you have m edges, there will be m such linear constraints. Let's stay a bit more with this problem, because it's an excellent introduction to another topics that we'll touch several times. Most problems that we cannot solve exactly, we still want to solve to get algorithms that will approximate them and to prove things about the quality of our algorithm. So I want to measure the quality of an algorithm that I want to produce by saying, I don't know what is C opt for this problem. C opt will be unknown. It's NP hard. NP hard in this course will be, for short, you can program it easily. You will not live long enough to see the program terminates for large enough input. Okay, it's a very short definition of what is NP hard. So I don't know what is C opt over here, but two approximation algorithm, or in the full name, is an algorithm with factor 2 approx. It's two ways to say the same thing. Factor 2 approximation will be an algorithm that produces some set C approx, set of C approx of vertices. C approx is a set of vertices, subset of the vertices of my graph, such that C approx is a vertex cover. That is, from every edge, C approx will have one of the endpoints of this edge in C approx. It still needs to be a set cover, but in addition, where is the approx comes into mind, what am I trying to minimize? I'm trying to minimize how many vertices have to serve on the set cover. It costs me $1 for every vertex that is serving on the set cover. So what I want in addition, I'm looking at the cardinality of C approx. Let's look at the cardinality of C opt. And let's look at the cardinality of C approx. C opt was the optimum that only some oracles or ILP can find for me. C approximate is something that I'll show you that is really, really easy to find in linear time. Obviously, C approx will not be the optimum. Optimum is the smallest set, but cardinality, it will not be smaller than this one, but the important requirement would be it's at most 2 times C opt. Okay, that's the important part. It's at most 2 times the cardinality of C opt. Okay, and the credit for the algorithm goes to Reuven Bar Yehuda. He was my master advisor. And before I continue, what is opt in this graph? Opt in this graph will be 2. Right? I can take B3 and cover it, getting rid of this edge, then taking B2 and cover it, taking B1 and cover it, and each one just remove one edge, and then realize that I have 3 more edges to cover, so I need at least 2 of them. Or I can start by taking B4, which is indeed a reasonable approach. And after taking B4, I'm left, after picking B4, essentially there is a bunch of edges that are already hit by this vertex, so I can delete them. I'm only left with this edge, and one of its 2 vertices must be there. So in this problem, it was easy. Now, aiming to get to a nice approximation, you can aim for find the vertex with a maximum degree and start with this. It makes sense, but it doesn't buy you actually anything for this particular problem. Usually, it's a very good idea in most problems. But here, I don't do it. So instead, here is a linear time algorithm. It's likely we'll start slightly deviating from the linear programming. We'll be back in the linear programming very soon. But here is a nice approximation algorithm for this problem. I'll pick an edge UV. From this edge, I know that I'll start, say, from this edge. From this edge, I know that in C opt, one of these 2 vertices must be in C opt. If you remember, that was the set cover that I got in C opt for this graph. One of its 2 vertices must be in C opt. So I'll take for where C approx is empty as an init. I'll pick an edge UV, add both U and V to C approx. And now not only that I hit the edge UV, I double hit it. I'm sure that it's well covered. So I don't need to worry about this edge. So delete from E. Well, I hit the edge UV. Let's say I'll start from B. I'll start from E3. and I pick both its vertices to be in C approx, which means that E3 is definitely covered, very well covered from both sides, but a lot of other vertices, a lot of other edges are covered as well. So delete from E any edge that is adjacent to U or V. So I deleted all the edges that are now covered. And if E is still not empty, then go to here and repeat until you hit all the edges. Okay. It runs in linear time. It's very easy to check how if you have adjacency list, you always check for every vertex who are the edges that touches it, and it's really easy to implement it. Now we need to prove why it's factor to approximation. Anybody sees it? Why is this a factor to approximation? Here are the vertices that I put in the C opt. These are the vertices that are in C opt. Yes?
So, in answer to your question of why it's like a two approximation, you're always...
It's factor 2. It's not more than twice.
Yeah. It's like you're adding, so at the beginning when you pick an edge, you add both U and V, but there's a possibility that you only need to add one of them.
Yeah.
And so for every, if you, in the worst case, it's every edge you add, like that you would need to put a vertex in, you add both the endpoints, and you wouldn't necessarily need to add both, so it's...
Well, it's not, there is a chance that it will give me opt, absolutely. Take this graph. If I'll start from E1, then I'm using these two vertices, getting from all these edges, and then I have to waste another one. But if I'll start from this edge, E2, and start from these two vertices, then I'm done. And the opt is 2 in this graph. So, but why is this never more than 2? So you're absolutely right that it's, and you kind of said it, but it could be opt. It could be that this algorithm produces opt. But why will it not be more than opt, or more than twice opt? Somebody on your face help me that you see the light.
Yeah, I thought Amy had it. So every time, anytime you're picking an edge, you add twice more than the minimum.
Excellent, yes. Okay, yes. So so if that's exactly what she said, I mean, if that's exactly what you meant, yes, absolutely. So we are looking at the opt. This is a set of vertices that I hit. Every edge, one of its vertices must be taken in the opt. What do I do in the most wasteful time? Instead of U1, I'll put U1 plus another edge, W1, the other edge. It maybe was unnecessary. But if I pick this edge that consists of U1 and W1, two vertices, then at least one of them I had to take for C opt. So in the approximation, I use 2 vertices instead of 1. Okay? 2. And that's why it's at most factor 2. We don't waste more than twice. Okay, back to linear programming. ILP. Everybody good with this algorithm? It was also a nice introduction to approximation algorithm in general. Most of the work in the algorithmic world is much more about approximation, much more than on exact algorithms. So let's change the game by tiny bit. Beautiful, beautiful example. Let's change the game a bit. Now every vertex has a weight associated with this. Some vertices cost $5, some vertices cost $3, and I want to pick vertices so that I'm getting a vertex cover. And the cost that I paid for the vertices that I bought is as small as possible. Okay? So I want to pick vertices. Now they have weights, each one its own individual weight. If they all have the same weight, it's of course the very same problem as before, but now if they have different weights, then I'm quite confused, and this approach, the greedy factor 2 approach, doesn't give me anything. Because if I have a very cheap vertex and a very expensive vertex and on the same edge and I take both, I might have paid way, way more than what I needed. And by the way, if you think that vertex cover by itself is too clean and abstract, it's not. With tons and tons of communication problems that finding independent state and vertex cover and clicks is really, really important and really implies lots of money, if you wish. Okay, to convince you that a vertex cover, that a weighted vertex cover can be solved as an ILP, here is our ILP. What's the difference between this ILP and the one that we saw one slide ago? There I was trying to minimize just the sum of the xi's, the number of vertices that I picked. Now I'm trying to minimize the sum of the xi. Every xi is 0 or 1. 1 if I use the vertex vi, 0 if not. Each one I multiply by its cost, and that's what I minimized. And the constraints are the same. Okay. So again, it was an example of the flexibilities that you're gaining from using ILP. You want to change a problem a bit, very easy to change. Now, why ILP takes lots of time? Let's play with this a bit. What is a scenario of ILP versus LP? Let's think about it in even 2 dimensions. 1, 2, 3, 1, 2. Here I have the grids of integers. I still have the linear half planes. Age 2, age 3, I'm still in 2 dimensions, but now I insist on the, say, the minimum, the lowest vertex, but it has to be an integer, which changes the game completely. If I insist that it must be an integer, then it changes the game completely. And it's possible that indeed LP might be, to solve the LP, no, without the ILP, might be a good starting point, and maybe I have a vertex, an integer, with coordinates 1, 1, or multi-dimension. Maybe I have a vertex very close to it, but maybe the linear constraints are just so well arranged, so the feasible region is somehow very slim and succeed to avoid a lot of integers. And here is one grid point that is in the feasible region. Here is the optimum of the LP, not the ILP, and they might be very, very far away. I'll ask you in the homework to give more, less hand-wavy proof about it. But LP and ILP are very different and might be ILP, obviously, once much slower. Surprise, surprise. And sometimes it doesn't give you a solution at all. So does it mean, so back to this problem. Is there any hope to get a factor 2 approximations? So surprisingly, yes. but not using greedy. We said LP, linear programming, runs fast. ILP runs slow, still probably faster than what you can implement in reasonable time, but probably, but obviously it solves NP-hard problems. So there will be scenarios that it runs in NP-hard problems. If anybody interested, hey, want to say, hey, we are living in 2020, there are neural networks, there are things. If you want to see publications about how neural networks are used to solve hard combinatorial problems like this, it's a very active area of research, of course. It's not that we are oblivious. Okay, so again, LP runs fast, ILP runs slow. If I remove the word int from my LP, it runs fast. So let's look at the weighted vertex problem. It's a weighted vertex problem, and so find the optimum float solution. That is, I took the ILP problem from the previous slide that says, I have the xi's, I'm trying to minimize the weights of the vertices that I take, and if xi is between 0 and 1, and I take the word xi must be an integer. And now I delete the word xi as an integer. Now I'll call it yi instead of xi, because I'll use it in the next formula. And I solve the very same problem. For every edge vij in the graph, yi plus yj should be larger than 1. Okay. And now it gives me a float solution. It could be that I'll still get xi's that are either 0 or 1, but it could be that I'll get values that are in between. Quick question. You're running the LP on this graph, A, B, C. What am I trying to solve here? I'm trying to find x1, x2, and x3 such that xi plus xj should be larger or equal than 1 for every I and j, every two vertices I and j here. What will be the solution that I'm trying to get? And of course, to minimize the sigma of the xi's. What will be the solution to my problem here? To the LP. Actually, it's not unique, but what will be the value of the minimum that will be unique? I didn't say integer here. So we all agree that 2 will be a solution. I can decide that x1 will be 1, x2 will be 1, and x3 will be 0, and it will be a cover. It is in the feasible region. I'm asking still what's the solution to the LP with the minimum cost, not the ILP. It will be 1.5. Absolutely. Agree? Every edge is covered if the xi plus xj is larger than 1. So stay with us, please. Does it mean, what am I going to do with this solution? Does it mean that, how do I want to know at the end of the day, take a subset of vertices, optimal or close to the optimal, with the weights, without the weights, but it must be covered. But these float numbers, how does they help you? Well, you'll be surprised, they do. So my approximation algorithm goes as follows. I'm going to solve the weighted problem. I call them yi instead of xi's because so I'll distinguish between them, but xi is just yi, over here. That is, if I used vi in my cover, then yi is a vertex associated with the vertex vi for every I. I'll solve the LP. For every edge, yi plus yj should be at least 1. And how do I define C approx? It will be all the vertices for which their variables is half or more. All the variables for which their vertex is half or more. If I have for some vi, it's yi is smaller than half, I don't use this vertex. Okay, so now I have two things to convince you. A, that what I'm going to wait for the vertices that I do use will not be more than twice. It still gives me a factor 2 approximation. And that I'm getting a cover of my graph. So why do I get a cover of my graph if I'm doing it? What in the LP guarantees that I'm getting a cover? It's possible that I'm missing some edges. Yes?
I think this is wrong. You do have a constraint that for any edge, one of its vertices participates. So I think that's the definition of the cover. So if that is one of your constraints.
But the LP, I take whatever the LP spits out. And I look at every number saying it's larger than half, I use it. If it's smaller than half, strictly smaller, I don't use it. Who said that the set of vertices that I'm getting is a cover? There is a chance that I missed some edges, that some edges are not picked by this set of vertices.
The constraint yi plus yj is greater than or equal to 1.
Look at this edge. yi plus yj is larger than 1. If y of 6 is smaller than half, and y of 5 are smaller than half, then their sum is smaller than 1. Right? And the constraint was that for every edge, yi plus yj is larger than 1, implying that one of them must be equal or larger than half. Great. So it is a cover. I hit every edge. Next, why the factor 2 comes into play. Why do I want to argue that it's factor 2 approximation? Now, what will be the cost of round of yi? Round of yi will be if it's half or more, make it 1. If it's less than half, then make it 0. Why can't I take just the ceiling instead of the round? Because, let's think about it. Here is the interval from 0 to 1. Here is half. If I have a value, if this is yi between that is less than half, and I'll still take this vertex, what do I know about wi yi? When I wi of this times round of yi. Wi times round of yi. If I'll take a vertex here, then if I will take it nevertheless, if that's a value of yi, say third, and I'll take it nevertheless, I need to pay 3 times what was its original value, But here, whatever the cost of this vertex is, since I'm only taking it from values that are at least half into a value of 1, if it's smaller than half, I eliminate it completely. Only if it's larger than half, I use it, meaning that by changing it from half to 1, I increased yi, but not more than doubling its value. So wi times round of yi is at most 2 times wi yi. Now at most doubled the weight. And now let's put it all together. What is the cost of C approx? It is the sum of the round of yi, the vertices that I take, the ones whose rounds gives me 1, times yi, times the wi, sorry. The cost of this vertex, how many dollars it costs me to use this vertex, which is, what did we say? It's at most 2 times, for each one of them, at most 2 times the sum of the yi, wi, but this is 2 times the opt, but well, what do I have right here? This sum of yi, wi is the cost of the opt. Here I'm talking about all the yi's, including ones that are smaller than 1. Still the round, it's true. This claim is true both if the round is 0, which is trivially the round is 0, then it's trivially holds, and both if the round is 1. So this sum of yi, wi is just the optimal solution to the float problems. And the 2 goes to here, so it's most 2 times opt of the float. And obviously, opt of the float is smaller than opt of the int. Opt of the int is the optimum to the real problem, where you are using integers. And of course, the float problems will give you better, cheaper solution. Why? Because you have less constraints. In the float problem, the LP, you're just requiring that xi is between 0 and 1. In the int problem, you are adding more constraints that it must be integers, so you need to pay more. So obviously, opt of int is more expensive than opt of the float. Right? So opt of the int is the cost of the optimum. The 2 goes from here. So we are getting the 2 times the cost of the opt is bounced from above the cost of the approximation. I think that it's kind of cute. You know? That's how LP help us not finding help us even if we really insist on an integer solution. There are scenarios that the LP still brings us kind of close to it. Okay, that's called the relaxation technique, by the way. And let's start a skip list. It seems that most of you know skip list, so we'll get a bit to the mathematical. I'll try to add a few points that you might or might not covered in 345 or taught it with me, but we can skim through it kind of quickly. And of course, trying to add things that are not on it. And after that, I think that we'll probably start with hashing. And I'll try to extend things that you covered in 345, 445. Just to remind you very quickly about what is a sorted linked list set of nodes. Every node has a pointer, a reference if you wish, an address of the next node in the list. We have somehow a pointer to the very first, the big element of the list. The last element points to null, points to 0. And if you don't like pointers, this is mostly for grad students, I hope. If you don't like pointers or reference, then you can think about all the next addresses as everything is stored in an array, and you have in the array cells that contain the key and cells that contain the index of the next element in this array. Pointers will just be the same, just the address in the array is the address in the real memory. OK, that would be a singly connected list. OK, nothing much about it. The head, the null over there, and we can move from one element to the other by following the pointers. And yeah, we can think about large array and so on. And we can make this list doubly connected. So every element has a previous pointer and the next pointer. So I can move backward and forward. Why would you like a list in general to be doubly connected instead of singly connected? Is that it makes adding and deleting elements much easier. If I'll just show you an element in a singly connected linked list, you cannot delete it without knowing who is the element before it. So doubly connected makes it a bit simpler to move to both directions. How do I search for an element if I have a sorted list? I'll start from the beginning. P will point to the head, and as long as P pointer key, the next element, this element that I'm pointing to is smaller than whatever I'm looking for, do P equals P next. And then there is a question, do you want to stop when you hit X, or do you want to stop one element before X? You can play with both versions. But if you will proceed only if the element that you're looking for is smaller than X, then of course, you can either do P key is smaller than X, or P next key is smaller than X. So you proceed only if the next element is smaller than X as well, and stops one element before. It's very convenient to add the minus infinity and infinity at the end, like one element with very large key, one element with very small keys that are not one of our sets. Why? Because otherwise, if you want to delete or insert elements, and the elements that we are inserting or deleting are the very last elements, they need some special treatment. These elements need special treatment if I'm inserting or deleting the first keys. If I waste tiny little bit of memory of storing two more elements, the code will behave the same for every element over here. And also it means that I don't need to check over here when I'm moving to the next element if the next element exists or I'm running into null. Because if P is null and you're doing it, then you will get core dump. You probably experience that you cannot, if P is null and you're asking what is its key value, bad things happens. Inserting a key in a sorted list. To insert 35, I'll allocate new memory for 35, place the key 35 around it. Before that, I'll find the predecessor of the 35, one element that comes before 35. Predecessor will be the largest element that is strictly smaller than the key I'm after. So for this, I'll have to do the search where I stopped just before I'm going too large. I'll find the predecessor of 35, this guy. The next is 37, and then I'm just arranging the next of the new guy and the next of the predecessor to put on the new guy. Right? Quite easy after the find. Delete 35, delete an element, 35, even easier. Again, find the predecessor of 37. You need the predecessor, not 37 itself. And the predecessor is 32, and 32 points to what comes after the deleted one. And then it doesn't exist anymore. If you are a good citizen and you're not using Java, you probably want to free this memory. Skip list. What rules about the skip list? Keys are all stored in level 1. Keys are stored in level 1, but also in other levels. There is multiple levels in the skip list. Lowermost level stores the keys, and it also stores, if you have auxiliary data, like the key is a student ID, and you want to store and the auxiliary data is a record of the student, it will be associated, say, only in the lowermost level. You want to store it only once. But a key might appear in different levels also. The key might appear in different levels with the following constraints. If a key appears in level 2, then it must appear also in level 1. You cannot appear in level 2 without appearing in level 1. And if you appear in level 3, then you must also appear in level 2 and also appeared in level 1. You okay? So if we look at the elements at each level, consider the set of keys at each level. Here is a set of keys that I actually use. Here is a subset of the keys over here. Level 2 is a subset of the keys over here. Level 3 is a subset of the keys over here. That is, it's a subset of level 2, and so on, until I run out of elements. Okay, and I still keep the infinity at the end, as before, and the minus infinity at the beginning, and I have a pointer to the leftmost first element in the highermost level. Okay. Every element has 2 pointers to the next and down. And how do I know that an element is in the lowermost level? Its down pointer is null. I'm trying to go down, its down pointer is null. -1, 0. The nil doesn't point to anything. Okay, here is an empty skip list. It's not the only way that an empty skip list might look like. You can look in other ways. But it might have more levels, but there is no keys. Still, the minus infinity and infinity are there. And how do I find an element in the skip list? Why does it work so nicely? So the idea is that I'm trying to find x. One algorithm is go to the lowermost level. Now you have a sorted list and go along this list until you find x. You can still do it. Again, go all the way to the minimum and scan the lowermost level, and it will take linear time, obviously. What are we doing with the skip list is that it allows us to jump over big chunks of data in one operation. If I'm sure that some cluster of data, some chunk of data is irrelevant for my search, I can jump in a constant time over all this chunk of data. The same way that in a search tree, going to the right subtree means I don't visit anybody in the left subtree because it's irrelevant for my search. And of course, I'll try to use as large jumps as I could. So I'll start from the uppermost level. I'm looking for x. Start from the uppermost level. Finding for 85, I will ask, is it safe to jump to the next element? Is it still smaller than 85? Yes. So I don't care who lives here. Jump over all of it. Jump over everybody that lives between this one and this one. Irrelevant, because it's still smaller than x, the next one larger than x. Go down one level, keeps the search over here. Not safe to continue, go down one level until you either find what you're looking for or find an element which is too large than what you're looking for, and then you try to go down one level, but you can't, so that's where your search ends. So that's a code that as long as you can move, as long as it's safe to move to the next one, that is p next key, is still strictly smaller than x, only then I'm moving to the next in the same level. Otherwise, I'm trying to go down if I could. Otherwise, I'll just exit at this point. Right? So that's the algorithm for the search over here in the skip list. And what's the beauty about the skip list is that even comparing to splay trees that are very simple, and comparing to AVL trees and red-black, it's so much easier to implement skip list, which you can do in a couple, 3-4 hours, maybe a day. Standardly gave it as a homework in cs545 to implement it in Java. Versus right rotation, left rotation. Left rotation of right location, zigzag, 4 cases, a lot of ifs and checks that A is a nightmare to implement, and B, to maintain or to understand is hard, and C, all these extra checks just makes the code much slower. Skip list just beats most of the other structures out there. There is a caveat that we are going to toss coins. It's a randomized data structure, but we'll talk about it later. Thanks, everybody.